taping anyway. All right. What's this guy? Oh, he's missing one. What's this guy? Yeah. Oh, we haven't seen these in a while, right?
It's a buckyball.
Cyclohexane, right? We've seen him before. Remember the chair and boat conformations of cyclohexane? But this ain't it. Look carefully. Put that away. Look carefully. This is not cyclohexane. Cyclohexane, if you remember, first of all, didn't have these double bonds in it, as you can see here, right? And he wasn't in a, look at this guy. He's all in one plane. Remember cyclohexane had a chair and boat conformation. Remember? All right, because it was able to partially rotate along those lines. These guys, this is a different guy. This guy is called benzene. And he is the backbone. He is the basis of what are called aromatic compounds. Pretty much all the aromatic compounds are going to have some benzene ring, that ring, in there somewhere. And it's a little different than, it's not just your typical cyclo compound in that it has these alternating double bonds, which we're going to find out are even weirder than you think. All right? Well, it turns out there's an entire branch of aromatic chemistry, aromatic organic chemistry. I'm just going to touch on it. It's our last day of notes for this chapter. We're not going to do any more new stuff until we have a test on Wednesday. All right? So I'm just going to give you a brief introduction to what aromatic compounds are, benzene, and how to name them. All right, but you're not going to get anywhere near as much. In college, you will absolutely, in organic, spend a lot of time on aromatic compounds because they're very important, as you'll see. All right, so. Yeah, didn't I give them to you yet? Okay, let me pass them out. Oh, they're not coming up the same way anyway. Hold on a second. I got to change something anyway. Here, pass these out for me. Here, pass those out for me. And I've got to change this guy anyway.
This is that.
This is going to be like a stranger thought. I can already feel it.
These two, Mr. Allen?
Yeah, those are good.
Thank you. Shit,
All right, y'all have this, all the papers now? Sorry.
This one?
Oh, no, just those two. Just those two. I'll give you your one out there. All right, y'all good? Aromatic compounds. They're all considered to be derivatives of benzene in some way, shape, or form. All right? Now, you have, this is the one day that the notes you have are not completely synced with the notes I have. I have slightly different pictures up here, and I'm going to have you guys draw a couple of things in here, maybe add a couple of lines, and do things a little bit differently. But basically, this is your benzene ring. Okay, it's the same thing you have here: double bond, single bond, alternating double and single bonds. But in reality, it turns out that's not what it looks like. I'm going to get to that in a minute. First, let me say a few words about aromatic compounds. All right. Oops, sorry. Aromatic compounds are kind of important. They're in more places than you might imagine. Like in your body, they're all over the place. They're in hormones, estrogen. They're in amino acids, several of them. They're in all 5 nucleotides of the DNA molecule. So, what are the 5 nucleotides of DNA? Adenine. Yes, you do. Yes, you do. Adenine, thymine, guanine, cytosine, and for RNA, uracil. Not myocil, uracil. Okay. So, my point is, you will find this ring structure, this benzene, they're considered aromatic. All right. You might say, well, the word aromatic kind of implies aroma. It's a smell. And it is true. Quite a few of these do have a very characteristic odor, and usually not an unpleasant one. That's where they originally got their name from. They noticed there was, I was reading about this just recently, it seems like the first ones that they found benzene rings in, Jacob, I'm calling you Jacob now, Jared. The first ones they first detected benzene rings and were doing experiments on were in things like what gives cinnamon its smell and wintergreen. All right, their smells. They have aromatic rings like this in them too. They have a benzene ring in them as well. And that was the first. That's why they're called aromatic, because it seemed like most of these things they're doing, they notice a strange compound in. And it's strange for a lot of reasons. I'll talk about that as we go along. Where they had a smell to it. But not everything that has a benzene ring has a characteristic smell. You are going to get passed around two of them today that do have very characteristic smells. But basically, not all of them do. Just happen to work out. That's where they got their name aromatic from. But they are really important. They're in your body. They're in a lot of things, and they're also used in production, for chemistry too. They're extracted from basically the refining process of oil or coal tar. So this, you get a lot of the stuff from a barrel of crude oil, people, not just gasoline. We kind of only think of it as being gasoline, but you get a lot of stuff from oil, and that's one of them. You get a lot of different aromatic compounds, benzene included. Okay, now, the first thing I want you to realize here is that these guys are not what they look like. And there's a lot of different ways I'm going to end up drawing these that are probably none of which are very accurate. You see, it turns out that not only can I draw this compound like that, but I could have drawn a double bond here and a single bond here. And you might say to yourself, but there is obviously a double of somewhere and a single in another place. And the answer is no. Turns out there's not. Turns out that, like we saw, kind of once before, we called it hybridization. Here we're going to call it resonance structures. There's more than one possible solution to this Lewis structure if you were to draw it. And so it turns out that no one actual structure really exists. If I were to measure, there's a way to do this. You're going to measure the length of these bonds and the strength of these bonds. Believe it or not, there is. Turns out that there's no difference between this bond and that bond, even though that seems to show a double bond. It's just as likely they could have a double bond here and a single bond there. And the actual bonds that do exist are kind of like a mesh between the two. They're called resonance structures, which is not a great term either, but they're kind of like a hybrid between the two. All right? So that's why we often can draw them multiple ways. And I want to show you some of the ways. To the side, I've got room, and I want you to draw these. So this is the one you have drawn right now on the top there, right? Draw this guy next to it. Sometimes I'll draw it like that. Notice I have the double bonds here. They're in a different spot than from that one, and we can actually, I think of them as resonance structures. Here, I'm drawing it like you would draw it on beaker, right? You're just leaving out the H's there, assuming the correct numbers are around there. But there's an even shorter way to draw it, which I will often use, too, with doing these. Okay, you want to see it? It looks like this. And this, believe it or not, may be the most representative, with the circle around it. Because as you can see from the second paper I gave you, and you look at the bottom of that, you'll see what looks like two donuts, or two life preservers, above and below this plane of a benzene ring on that paper. Okay? And that is probably a better representation than either of these, because it's showing you that you really don't have a double bond here and a single bond there and a double bond there and a single bond there, but rather it's like a mash together somehow. These electrons are what we call delocalized over the entire ring. All right, they're shared between them, between these atoms, and such that these bonds are incredibly much more stable than they should be. This is what made this guy weird to begin with. What they were finding out, it seemed like it was unsaturated, yet it wasn't very reactive to addition reactions. It wasn't as reactive as it should be. We're going to get to reactions next chapter. I can't wait to talk about that now. But we're going to find out that a double bond, being a region of very high electron density, is going to attract positively charged guys. Okay? And they're going to attach onto them. Well, for some reason, benzene is pretty stable. He's very stable. Okay? And that didn't make sense to them. They didn't know what the structure looked like. They finally came up with this structure of why this happens. And it's because the electrons are kind of shared across the ring in that donut kind of formation you can see. You can read that paper. It explains it a little bit. All right, so let me just say in words what I've been kind of saying all along here to describe the benzene ring. All 6 bonds, like I was saying, are identical. That doesn't seem to make sense, but they are. They're identical because the electrons are basically shared. No single structure is going to represent this guy. Electrons are shared across these guys, and no single structure can represent it. So we use what are called resonance structures. And I have a drawing for you. Yours is, again, this is the one day of notes, I'd say, for the whole, all of organic, probably, where things are not exactly like your paper looks. So I'm having you kind of ignore some things, draw some things, add some dashes. You're going to have to do a little bit of all that. The next picture that's going to come up here, you have the same basic picture. It's right down below where you just wrote. But I have it vertical instead, you have it horizontal. It's what we call resonance structures. Okay? But the reason I don't like the word resonance structures, and I think most people don't, is that see this one, yours is sideways. Okay, you see that below it, where it has an arrow between the two. I have an arrow between the two. All right, the reason there, see the double bond's here, single bond there. Now it kind of implies that he's flipping back and forth between these two groups. He's flipping back and forth between these two guys. That's not really what's happening. It's much more so like this thing here, which you have drawn above. I had you draw a circle on the inside of that, okay? So in reality, these guys do not flip. You need to add this below that guy, okay? And then you're going to have to add something to the left of that circled one below. Right there in that dash. Okay? So in reality, it doesn't really flip between these two structures, but rather contains a hybrid bond of electrons that are delocalized over the entire ring. And that makes it more stable than it would be having all these double bonds in there. Okay? Now, like I said, you're kind of running out of room here. Where I have that little redrawing underneath it, on your paper, it kind of like is down here. You have this guy down there. Okay? Well, to the side here is where you can put these next notes here. Yeah, I should have enough room there to the side, right? All I want to do there is start. Now, hopefully you understand a little bit about how weird these guys are, a little strange, but I need to, remember, I'm not doing a class of aromatic organic chemistry. It's going to be kind of, a little bit more detailed than what we need to. We'll see it one more time when we talk about reactions, because they do show up. They even show up a little bit in polymers when we talk about that in the following next 2 units. But right now, let me just give you an idea of how we name them, because they're not going to be named the way you might think. I mean, I could call this 1, 3, 5, right? Cyclotriene, right? I could call it that, but it's a heck of a lot easier to call benzene. And that's what we're going to do. Okay, so I want to talk about the naming, how we're going to name these guys. So write this right to the side of that little guy there. I know there's not a whole lot of room, but above example 1. So they're named basically the same way alkanes are named, giving the substitution groups the lowest possible numbers. But we're going to use benzene as the parent name for these guys, okay? Instead of like 1, 3, 5, or cyclo, whatever. It just gets a lot easier to use as benzene. So let's do that. And I have room for some examples down there. I'm going to do 2 examples. Again, we're getting to a place where your thing's a little off. Don't draw this yet. I have chlorobenzene right underneath it, and then I have underneath that one, I have your picture of methylbenzene. Okay, I did them sideways on here so I can put them on the same board. Okay, so for chlorobenzene, no surprise. Chlorobenzene looks like this, and you have basically that picture drawn there for you. Although I use this format, you used, I think on that other paper, I used a circle in the center of it. That will be chlorobenzene. What if I put a Don't do this, but what if I put another one on here? What would that be? See, I didn't have to put 1 in front of that guy, but if you did, I wouldn't take off. But what would I call that guy now? 1,2-dichlorobenzene, you see? Or if I had one down here, 1,3, okay, all right. And what do you think methylbenzene is going to look like? I don't think anybody would be too surprised by this. That's methylbenzene, right? And again, how else could I draw these guys? I could have just drawn it with the circle in there, right? Or I could have drawn it all the way out. Oops, that's too many. You know? Do be careful. If you do draw a guy all the way out, how many H's are coming off of this guy? Only 1. Not like cyclohexane, who is going to have 2 because there's no double bonds around there. All right, so there's a lot of it. This way, that way, that way. There's a lot of ways I could draw it, basically, if I had the methyl. And by the way, notice I drew the methyl over there. Does that make him 2-methyl? People still get that idea that the top is number 1. Where's the number 1 carbon in this case? Right there. Whoever the guy's lowest possible number, right? Okay. By the way, one other thing about that guy, he is called toluene. That's his common name. That is not one. I don't make you memorize a lot of the common names, but there are several. Benzene, toluene, and the next one, xylene, you're going to get, which are so common, so used so often, that you kind of have to know these. Another one you're going to get to when we get to some of the reactions, the different kind of functional groups. I've said this one before. No one really calls ethanoic acid ethanoic acid. We call it acetic acid. If you get a bottle, it almost always says acetic acid. Okay? There's a lot of things like that. Formic acid, butyric acid. We don't use the systematic name for naming these guys. The real name for it is ethanoic acid, we call it. The real name for this guy is methylbenzene. But if you were to buy a bottle of it, you know, if you're working in a chemical lab, you're not going to buy a bottle of methylbenzene. It's going to say it on the bottle somewhere, but it's going to be toluene. That's how it's going to. You know, that's why I'm going to make you know these common names, the few that I have. All right. Now, there's another version of dimethylbenzene I want to give you here. That's on the next page, but I don't want to give it to you yet. I'll give you that page in a second. There are actually 3 structural isomers of methylbenzene. You might think, well, no, there's probably more dimethylbenzene. There's got to be more than that, but there aren't. Let me show you. Oops. Let me draw a dimethylbenzene. Okay, what would I call that guy? What would his systematic name be? 1,2-dimethylbenzene. What would this guy be? 1,3-dimethylbenzene. And this guy, I'm going somewhere with this, trust me. What would this guy be? 1,4. Okay, well, aren't there more than that? Like, for example, what about this guy? Is that a different one? No. He's exactly the same as that one. And if I erase him here and put him over here, what's he the same as? That one. Okay, so there are only 3. But they have special names. And they're prefixes that are used here that are actually very common. Used in a lot of different things. Okay? There are 3 structural isomers of dimethyl. You don't draw these. They're on the next page. We're coming around to you. All right? They look like this. I just drew them on the board there for you. There you are. And we're going to name each of them 2 different ways. The way we just named them, as the UPAC system, we named them. And with the common. Okay, according to the UPAC system, you could name them as we just did. I want you to. 1,2-dimethyl, 1,3-dimethyl, or 1,4-dimethylbenzene. But the other way they're named, and their prefixes are commonly used, are on your paper there. Ortho, meta, and para. Orthoxylene, metaxylene, and paraxylene. Not paraxylene, paraxylene. Ortho is when the two groups are next to each other. Meta is in the middle position, and then para is opposite. Okay? And those prefixes, I used to do this as a extra credit thing. I don't do it anymore. But I used to say to kids, usually after this chapter, no, usually outside this chapter, the next chapter. After the next chapter, I'm usually able to say, used to be able to say, I'll give you points for all of the household chemicals you can name. You had to bring me the labels from anything in your house. And if you could name it could be medicines, it could be household cleaning products, it could be lotions and hairsprays or whatever. And there are a ton of organic chemicals in those things. You ever look at your hair conditioner or shampoo? I mean, the list is like, as long as your arm of all the organic chemicals in there. And what you'll find is, if you read that list, you will find the prefixes ortho, meta, and para in a lot of those things. They tell you the positions that these groups are on. And as we learned what these groups were, whether it was methyl, ethyl, propyl, we learned about that already, or other things, you're going to learn about some of the new suffixes, you were able to put them together and give me, and people would be able to tell me and draw the structures for these things in their everyday household stuff. Why don't I do that anymore? I certainly can. I don't want to. No. Well, that is true about getting in trouble. Of course, I have people bringing in their bottles of Jack Daniels because it's got ethanol in it. That would be true. That would be a bad thing. But no, I don't do it now because it's so easy to get the answers. Why? Yeah, you just Google it. If you just type in any one of the chemicals, you can type in every single one of the chemicals in your thing, and it would just give you the formula. All right, so yeah, that's why I don't do it anymore. I wanted you to be able to think about it, to apply the prefixes and suffixes and all the stuff that we've learned. But now it's just so easy. All you would do is type it in, and you can get every one of them right. So I don't do that anymore as an extra credit thing. But these prefixes show up all over the place. Let me show you a place where they show up right here. I'll pass some of this around. I always like this class comes around the fair break. Okay, because this smell reminds me of the fair. This is, well, you're going to tell me, the camera, I don't think I see this, but read me the, well, first of all, smell it. Don't smell it too loud. You don't have to smell too loudly. Don't smell too loudly! But read the active ingredient. You can smell it. Exactly. Read that for me. You can hold it. Go ahead. What does it say is in it?
Chlorobenzene.
Yeah, keep passing that around, and we'll draw Chlorobenzene on the board here. All right. What do you think Chlorobenzene would look like? Yeah. Right? Everybody agree? And that's what's in there. Now, what does that smell like? And why do I think of the fair? Guys should get this right.
I don't know.
Exactly. I said guys should. You go in the guys' bathrooms? That's true. They use the same stuff. It smells like those urinal cakes, which I always love about the fair. Here I am at the fair, and girls don't know this, but guys go into the bathrooms at the fair, and you're peeing in a trough. There's a trough the length of the wall. You know what I'm talking about, right? And then someone's asking you for money so that you could pee in that trough. There's always somebody sitting there with towels asking for money. You girls have that too? Yeah. It smells so great in there, though. I mean, that's Chlorobenzene stuff. It's the urinal cakes. But it does smell like that, doesn't it? Yeah, it's pretty. Now, of course, nowadays, it does remind me of the fair. That and those guys playing those flutes and stuff. I love those guys. They're so good. Agua Clara. Anyway, all right. Now, the last thing I want to put together for, you can put that on the radiator when you're done, so we can all smell it. Have it blow up. No, don't really. The last thing I want to mention about benzene rings is that they can also be fused together into longer, almost like chicken wire, And you can see some. I can show you some pictures from. I will get down one of those CRCs. I mean, these things can grow into very long chains. Okay, fused ring structures. It's on the next part of that paper there. And I have an example of that one. First of all, their benzene rings are attached at 2 carbons apiece, not just 1. And here, I have another thing to pass around for you. I don't know if you think, I think this smells better than the other ones we just had. Take a little whiff of these. Tell me what they smell like.
I guess they smell like
Ah, good. Very good. Attic. Old people, yes! They smell like old people. That's how they make them. They grind up old people, and they make them into naphthalene. That's what you get from old people.
Probably. I can believe that.
It smells like my grandparents.
Yes, it smells like your grandparents. Exactly.
It smells like their basement.
Well, that's where they are. That's where your grandparents go, right there. There's a lot of grandparents in that
Or it
box.
smells like a furnace, kind of like a...
Yeah. It smells like the basement or the attic or your grandparents for a reason. What do you think they used, your grandparents used mothballs for? They did not use it for perfume. That's a good answer. I know it's hard. Josh, you don't need to keep smelling it, okay? Just keep passing it there.
I have pass around things.
You're not huffing this
smell
stuff.
Why not?
I gotta put those away. Alright, what did your grandparents use mothballs for?
Moths.
To kill moths, exactly. To keep them away, anyway. See, I know you girls can't imagine a world where you wore, like, you had, like, one Sunday dress, and you had one good sweater, and if you're a man, you had one suit, and you kept that suit your lifetime. I mean, basically, you almost never got a new one. And they were made of wool, and they could be eaten by moths. And so they would store them with mothballs around or in cedar chests to keep away the bugs. And that's why your parents or grandparents, well, at this point, probably only your great-grandparents still use these things. That's why they smelled a little bit like that. That's why your old house, the old attic smells like that, to try to keep those things away. Anyway, that's what naphthalene looks like. I think that's a picture of it right there.
Why?
Okay? And the thing is, I can keep growing this. And I'll show you that, a picture from the CRC in a minute. Here, for example, is anthracene. Look at anthracene.
Maybe auto control this.
Yeah. Well, no, it's already there, isn't it?
No.
Oh, well then, yes, you have to draw. And how hard is that? All you got to do is be able to draw lug nuts.
I can't do that.
That's what it looks like, doesn't it? Look at it. And then don't forget to draw your wrench.
Oh, I screwed up. Oh, wow. Such good bad. Josh. Look at this. Look at this.
There you go. Craftsman.
Oh, wow.
See? Wait, I got to loosen that one. It's a little tight. Wait, righty tighty, lefty loosey?
It's really bad.
So, anthracene, also known as triple lug nuts, is up there on the board.
No.
No. Yeah, calculate the torque on that one.
No.
What the hell is torque?
That's fun.
It's a race of people in Star Trek that works.
That's like when he said torque. He said torque is for rotation when you have a lot of force.
Racket.
I want to show you this. You know, we don't use these much anymore. These are called CRCs. But just to give you an idea, in the CRC of how these fused ring structures can get a little out of hand. I mean, you can see how they get really, really large.
They get really large.
Yeah.
I think it just like squiggles.
I mean, some of them are pretty crazy.
Pretty crazy.
They look like chicken wire, basically. And by the way, this does illustrate one last point before we... I know. No, they don't smell like moths. They smell like moth balls.
They smell like moth balls.
Wait, that doesn't sound right. But anyway,
They smell like...
It's fast as my